Light bounces off objects in a similar manner to the way a tennis ball bounces off the ground or other surfaces. Unlike any tennis player will tell you, the ability to predict where the ball will go next is central to the success of the player. This bouncing off of a surface of a wave is called reflection. So let's learn how to predict the path of a wave being reflected. The diagram on our screen represents a ray of light reflecting on a plane mirror. The incident ray is the direction in which the light falls on the reflecting surface. The dashed line is a line perpendicular to the reflecting plane at the point where the incident ray meets the mirror, and this line is called the normal. The reflected ray is the direction the light moves after leaving the reflecting surface. All these lines, incident ray, reflected ray, and the normal, meet at a point known as the point of incidence, labeled O in our diagram. Now the angles I and R. The angle I, made with the incident ray and the normal, is called the angle of incidence, while the angle R, made with the reflected ray and the normal, is called the angle of reflection. These laws of reflection state two things. First, the incident ray, the reflected ray, and the normal at the point of incidence all lie in the same plane. What this means is that the ray of light does not change direction and leave the initial plane that it was in. That is to say, its motion can be completely described in two dimensions. The second law of reflection states that the angle of incidence is always equal to the angle of reflection, which means from our diagram, I is always equal to R. It follows that if I is equal to R, then R is equal to I. Hence, if the direction of light were to be reversed, the path followed will still be the same. This is known as the principle of reversibility. An experiment can verify this. To do this, we need 4 pins, a ruler, a white sheet on a drawing board, and a strip of a plane mirror. So let's begin. Lay the mirror strip on its edge along a line MM' on the sheet of paper and mark a point O in the middle. Then draw a line ON perpendicular to MM' from the point O. Line ON is the normal line to the mirror plane MM'. Next, draw a line OA to make an incident angle I of 30 degrees to the normal, and place 2 pins P1 and P2 along this line, a distance of at least 6 centimeters from each other. Then go to the other sector of the normal and try to view the reflected image of the 2 aligned pins. Once this image is seen, place the 2 other pins P3 and P4 along the line you can see. Now draw a line from OA' through the points made by P3 and P4. The greater the distance between the pins, the greater the accuracy of the lines. The angle between ON and OA' is the reflected angle R. Repeat this process for incident angles of 40, 50, 60, 70, and 80 degrees, and make tables of the angles I and R, and what you would notice is that for each case, I is equal to R. Now here's a simple application of the law of reflection. Supposing we fix the incident ray still at an incident angle of I to the normal, the total angle A between the incident ray and the reflected ray is I plus R. But R is equal to I, so the total angle is 2I. Suppose we then tilted the mirror by an angle theta. The incident angle increases by theta and becomes I plus theta. The reflected angle also becomes I plus theta, making the new total angle B to be 2I plus 2 theta. The difference between the first total angle A and the new total angle B is 2 theta. Therefore, we can say that the reflected ray always rotates through twice the angle through which the mirror rotates. Now that's a lot on reflection to reflect on. Keep learning.